this is a summary that we had last week. From you have really like for MOSFETs, we have two types of equivalent circuit. So the one that the pi model is the simplest one that you have VGS at the input side, and you have a current source, which is GM times VGS. You remember GM is 2 times ID over VOV, and then this RO is equal to VA over ID. So those are the numbers that was given. From this model, it was easy for common source amplifiers, but getting to common source amplifier with the resistance at the source, it becomes more difficult, or emitter followers or common gate. And this model, even though it works, it just becomes more complex, right? So we then, to simplify our life, that we developed a pi model, a T model from pi model, and we went through process how to derive the T model. And in the T model, if you see that between gate and the source, there's a resistance called 1 over GM, and that's the one that we derived. And then the current source didn't change, still GM times VGS. And then there's RO. Remember, just there's one thing that students often make mistake, that they connect RO between drain and the gate. So that is wrong. So it should be connected between gate, between drain and source. So that's the thing. Now this circuit, the last circuit here is just the duplication of this one, but rather than like a voltage as the input VGS, it uses I, right? So this you see it becomes I, and this becomes I. So this is simple to understand, because if your current coming in here, that's I, and then you have current coming here because there's no current at the gate. If you use I times I over GM, what do you get? Right? You get the voltage, which is VGS. So that's exactly what you have. So VGS divided by 1 over GM gives you I. So that's how you get this equivalent circuit. So that's for the MOSFET. So in the future, we're going to, starting from today, we talk about various kinds of amplifiers. Every time you say amplify, go grab that transistor, replace with a model. You can choose between either one of this, depending on the circuit configuration, and then so for the circuit. So this is what I wanted to get you guys really learning the methodology, other than just the how. So the methodology itself is to make it your life very simple. You understand the procedures, you understand how to do it, instead of focusing really heavy on the mathematics, right? So this is very important. You follow the procedure, you be careful with the numbers, you'll never make a mistake. Right? So this is the MOSFET. And then when we get down to BJT, it's almost identical, except that the pi model, you have R pi. And the calculation of the R pi is given here is beta over GM. That's the one that you probably have to kind of memorize that. And from that, you can translate to RE, which is alpha over GM, because pi and RE, they have a difference of alpha. Okay. Now, if you look at the top, we have the model, which is this one is most popular one, with R pi with VB input and GM times V pi, so that you get the current, and is RO. RO is VA over IC, so that's the one that you got. You have to calculate. So in that circuit, R pi, GM, and RO, those are the three things that you have to calculate. But those, of course, are easy equations to remember. But you don't have to remember, but you can write it down and also know where to find it. Similar to the MOSFET circuit, if the pi model sometimes doesn't work very well, so we transfer that into a T model. And in the T model, you have simply RE over here. And that RE is also similar to 1 over GM, which in this case is alpha over, is a beta over GM. No, RE is alpha over GM. So alpha is almost 1, right? So it's almost 1 over GM. So that's similar. The circuit over on this side is really just transferring, instead of using voltage as the input, it uses a current as an input. So you have a current here, so this becomes alpha times I. Right? So because what your GM is alpha and also related. So this becomes alpha I, and this becomes I, this becomes IE. And similar to that one is instead of that IB, instead of GM times V pi, use beta times IB. I mean, you know that GM is what? GM is given somewhere IC over VT, right? So, and then that's exactly all related to different relations. So keep those 2 pages handy, then you'll find them very useful. When you get to problems, you don't have to flip your book and look for where the equations are, right? So from here, then we can jump to section 3. Just look at the basic configurations. Because we have 2 more sections. Section 0.4 talks about biasing, and then section 7.5 just dive a little deeper into the circuit configuration where you have low pass capacitors, things like that. We're going to get a little bit of those when we get to that chapter. So there are 3 basic configurations for each type of transistor, and this is for MOSFET. So again, we already mentioned many times what they are. So if you look at from left hand, when the source is grounded, we call it a common source. The common word comes from the input and the source. They are both grounded, so they have a common ground. So think about it. It's a common ground, right? So they share the same ground. So that's why it's called common source, because the source is grounded. The input is, of course, input one side is also grounded, the other side connect to the gate. So this is common source. And then the middle one, instead, we ground the gate and we connect input at the source. So this becomes a common gate because the gate is grounded. Now you might ask, how about the drain? Well, the drain is not grounded because the drain connects to RD. That RD is grounded, so it's not strictly, the drain is not grounded. So that's why it's a common gate. And the last one is common drain because in this case, your drain is actually grounded. You look at up, the drain is actually grounded. So your input is still at the gate. Where's the output? Well, your output is at the source. Okay. Now, this circuit per se, it doesn't include the DC. If you look at it, we didn't include DC. So this is basically more like a small signal equivalent circuit. Okay, just we didn't use actual small signal like the amplify, the circuit, but we still use the symbol of a MOSFET, but we removed all the DC biasing, like the power supply, the DC bias, the gate biasing, and so on. So we assume that every transistor is in a saturation mode, and we only included the AC parameters, no DC. So for each of this one, you probably can already think about it. Well, this one, I can simply use a pi model, but this one, maybe not, because if you use the pi model, I mean, what I can do is we can probably go through each of this and we can simply draw the models and see how they look like. Again, as I said, it's just not the end of the world. You can still do it. Yeah.
Why is this called source follower? Like, what is that?
What is
the verbiage? Like,
the source follower is here. This one is called a source follower. The reason it's called a source follower because output is almost identical as the input. So it's like a follows the input. When input changes, output changes same way. So the value is almost the same. It's like 0.99. So they try kind of follow. The source follows the input. That's why it's called source follower.
Okay. Is there like a mathematical reason?
Oh yeah, because the output is the same as the input. For MOSFET, it's called source follower. For emitter, same thing, emitter follower. The output at the emitter follows the input for AC, right? So we're going to get to that. We're going to get to that, okay? You're going to see. Mathematically, you're going to derive the equation, so it's almost identical. And of course, you might say, oh, if it's identical, why do we need it? Well, we're going to talk about that as well towards the end of this section, because you need to increase the input resistance and lower the output resistance. And we mentioned that many times. So okay. So we just do a little bit of digging here before we move on. So for the common source, like if you identify where the MOSFET is, right, and then you can replace that with a pi model, that's apparent. So we have And of course, here is we have this RD. So you can easily find out, well, the output VO is going to be GM times VGS, in this case, is same as VI, times the RO in parallel with RD. So, and then you're going to need this minus sign here. Okay. So that's very simple, right? Common source. And then the middle one, we're going to draw the equivalent circuit, but we're not going to solve it because we're going to solve it later anyway. So let's just start with the pi model. So if we draw the pi model, you see what happens is the gate is going to be grounded. You know, like what I told you guys last time is to identify the MOSFET and draw the small signal equivalent circuit of that amplifier and then connect everything to each of the terminals. In this case, you have the gate grounded, yeah, and you have the drain connect to RDs through RD to ground. So you have that one is done. So, but then where is the source connected? Well, the source is no longer grounded in this case, but actually it's connected to input. So what you're doing is you have an input connectors to the source. Yeah, that is a way of looking. But you know what? No, actually, I made a mistake. So I connect here. Okay, sorry. The current is not flowing to ground, so that was a mistake that I made. So the important point is that VGS is right over here, is between gate and the source. But this circuit actually it's not, I mean, it's not that bad because you can still figure it out that the voltage VGS, in this case, VGS is the same as VI, but opposite direction because this is the middle. So this VGS is the same as VGS opposite. So VGS equal to minus VI. And once you know VI and then GM times VI, GM times VGS, which is minus VI, you get the current, and then that current flows through these two resistors, and you get the output. So this one, actually, we could use the pi model, no problem. Of course, you can always use the T model. But in this case, you see, we always going to be GM times VI negative, and then also negative, and then negative RO or RD. So that one is actually give you, it's a plus. So maybe I just neglect the plus sign. So it's actually GM. So you see here the difference between these two. Yeah, for the common source and the common gate, you get the output is almost similar, but in the common source, the output is negative, but for the common gate, the output is positive. Yeah.
So we don't have to worry about, like, when we're measuring the VGS, it's from like the top to ground, right? So I think, like, what about the voltage drop across the current source there? Do we have to add that in to make VGS our output?
No, this is the ground. So this is your voltage. You're measuring between these 2 points. So the total current goes here. Yeah, no, this is VGS times GM. So the total current flowing this two, so you got your voltage output wheel.
Oh, so what's the formula for VO again?
Yeah, VO is current times resistance.
Oh.
Yeah.
Okay.
Yeah, but it's negative.
But
Yeah.
okay. VGS, how do we find VGS?
Well, VGS, because this is the middle. So if you use loop analysis here, you'll find VGS same as VI, but opposite direction.
And is the current source not part of that loop?
No, because you're looking loop here. There's nothing to do with this side.
Very strange looking circuit.
It is.
Okay.
All right. So for the last one, I'm also going to use the pi model, just try to show you guys how this is going to change. So the pi model starts with this, and you have RO, and then, but you have this one grounded. So this, you have the drain is grounded, okay? So now we have input connected again at the gate, which is okay. Where we are connected. The only problem is that we have our L connected over here, and we measure our output over here. So this is critically important where you see where you measure VO, because this is grounded, so we measure VO over here. So your VO is really just current flowing this way, right? So your current flowing to RL, you got this VO. But the difficulty of this one is that this GM times VGS, this GM times VGS, this is very important. Is VGS is not equal to VI. The VGS, you see, sometimes people kind of look at, oh, VGS VI, they are kind of like a VGS VI, right? Or VGS same as VI? No, that's not, because this is not ground, but this is ground. So your VGS is actually what? Your VGS is actually VI minus VO. VI minus VO is your VGS. So what is your VGS? So your VGS is VI minus VO. Okay. So and then in this case, and what is your VO? Well, your VO is GM times VGS times GM times VGS times RL. So if you plug it in this one here, you can solve. You replace VGS, right? So with a VI, and you have VO on both sides, and then you can derive your VO. So we're going to derive later, but just so you know that this model, you can still solve the problem, but just that be careful that VGS not VI, VGS actually VI minus VO. So, but then of course the voltage over here is what? Is RL times this GM times VGS, right? So you go from here, and it's those two equations will give you, you will be able to find VO, and then once you find VO, you'll be able to find the voltage gain. Okay, so. So that's our that's our MOSFET amplifiers. And then we move on to BJTs. We got the same thing. So you have common emitter. What does it mean? Well, the emitter is grounded, and the input is also so the input has its ground, right? So this one has the emitter, and the input share the common ground. So that's why we call it a common emitter. And in the middle, we have common base, because the base is grounded and the gate is grounded. I mean, the base is grounded, and the input is at the gate. So you have a common gate. So gate is grounded, so they share the common ground. And in the last one, we have common collector or emitter follower. What means is that the drain is grounded. So the input and the drain share the common ground. So that's why we call it a common collector. And in the future, you will understand that this is also called emitter follower. So for these three configurations, we apparently can also easily use the pi models to find the gains. So we can start with the common emitter one. You have, again, find the transistor and replace that with the pi model. Now, in this case, the difference is that So you guys notice this is almost identical circuit as MOSFET. The only difference is that you have RPi instead. But that doesn't really change anything because the circuit over here is identical and the circuit over here is also identical. So you have V pi equal to Vi and your output will be like the current times the parallel of these two resistors. So you get that quite easily. And similarly, you can draw the equivalent circuit of this one or this one, because let's do that later. Just give you a flavor right now, saying, yeah, you can use a pi model to replace the BJT of each one, and you can draw the equivalent circuit, and you'll be able to find the output. So that's kind of the simple process. And then as I said, we're going to derive those later instead of right now. I have the page corrected. But before get to that point, I want to just review some basics of like a generic amplifier. Because so far you see, you have BJT, you have MOSFET, both can serve as an amplifier. And for each amplifier, you can have 3 different configurations. So there's 6 of them right now already. But at the end of the day, all the amplifiers can be generalized to one simple model. And that simple model says that you have input, and then of course your input might have some internal impedance, we call it RSig, and then the middle is your generic model. You have input resistance, you have output resistance, and you have and then here we have a voltage gain, but you can also change this to a current gain, okay? So, and then you have load resistance. Over here, the reason this generic is important because here we identify a couple of things. So first of all, that R sig, that's the source resistance. So that source resistance can impact how much your gain can be, because the amplifier gain is not your actual system gain. So your system gain really depending on, I mean, it's highly related to R sig. You know, for example, let's do example. If R sig is 1 meg, R pi, we call it R in here. So if your input is resistance is 1K, but the input resistance of the amplifier, and your R sig is 1 meg, how much do you think your all gain will reduce? Well, what it says that if you now you can solve for this circuit. So this is 1K, this is 1 meg. How much voltage we are? Is 1 over 1,000. So your gain reduced by what? 99.9%. So regardless of your middle, like your amplifier gain, your actual gain will be much smaller because your I sig is too big. So in this case, your gain reduced by 99.9%. Now, of course, if your R pi is 10K, you reduce by, if R in equal to 10K, A we reduce by still 99%. So you guys can think about it. For BJT, R pi equal to roughly 10K or maybe 5K, maybe 10K. So that's the typical number. So in this case, you would want your input like R sig to be small. So if your R sig is 0, your gain doesn't reduce at all. So it's all passed through. But if your R sig is very big, your gain is reduced by a lot. But so the other thing, of course, to do is to increase the input resistance. So if RE is increased many, many times, what happens? Like if if R6, I do the flip, is 10K, but your R in is 1 meg. How much overall gain is going to decrease, do you think? Overall gain will reduce by, because your input is 1 meg, 1 meg plus 10K. So it's really reduced by what? By 1%. Right? So 1 meg over like 1.1. So it's about 1%. So if your input resistance is very big, regardless of your R6, your gain wouldn't change very much. Which device has that property? Which is MOSFET. MOSFET has input resistance how much? Because we have MOSFET, remember, our MOSFET is like this. So R in is infinity. It's open, like there's no current going into the gate, okay? So it's infinity. So for MOSFET, the input is really good. So that eliminator of the R input is not only simplifying your overall like analysis, but also actually have some really advantage is that it has infinite input resistance, okay? And of course, for this circuit, we can also draw this as a current source. Okay, so these two circuits are equivalent to each other. Now, what I added is well, let's remove this one. So these two circuits is really identical. Now, from these two circuits, you can transfer each other. Well, the reason is very simple because this is a voltage source, right? So you can transfer that voltage source into a current source by source transformation. So it will become a current source multiply in parallel with resistance. So these two are identical. So in the future, you'll see, okay, this, it doesn't matter, like you already have current circuit. So this is a generic amplifier. Now let's look into a few things. So now you already notice that what's important for the like input resistance. So the larger the input resistance, the better for your circuit. So we want the input resistance to be big. Now, how do you make it big? Well, first of all, you can choose MOSFET. That's something you can do, right? But if you choose BJT, use a common source, you're out of luck because that's given. But we can use a common collector. When you use a common collector, this number increases dramatically, and we're going to see that as well. So that's why we're talking about different amplifiers. When this increases dramatically, this number is irrelevant because this is very big, okay? So now let's go into, say, next step. How do you find like how do you find RO for the amplifier? Because if you cannot find these two, you cannot solve the circuit. And then for different amplifiers, and these two numbers are going to be like, we have to find them by doing circuit variations. So like if you want to find, let me see, right? Yeah. So if you want to find R in, is for any circuit, what we do is we inject a voltage and we find the current. And then so from here, we find our input is equal to V in over R in. And in this process, of course, for any like black box, you would just, if you don't know anything, just inject a voltage, or you inject the current, measure voltage, or apply voltage, measure the current, and you get input resistance to be that way. Now, in that process, what we are doing is you're going to careful is to short any voltage source, open any current source. So let's give it a try. The top is a generic amplifier, and this is our equivalent circuit. So in this case, we want to find out the input resistance. We want to find the input resistance. When we find the input resistance, as I said, what we do is we short the voltage source and current source, but then we also we just apply. So this is our amplifier. So what we're doing is we're going to apply now. What I'm going to do is I'm going to use the more generic one. So you guys. Yeah. So the middle one that I circled is our amplifier. So we take the amplifier, we apply a voltage. So in this case, we can find I in directly equal to V in over this R in. So in other words, your R in is equal to your, what do we say? It's R in. It doesn't really matter because this is your input resistance. So yeah. Well, I mean, I should have used a different symbol, but in any case, I used R like something, we should do a different number. But you see,
That makes sense.
you have all this circuit here. It doesn't impact the input resistance. Why? Because it's a separate circuit. And what you're doing, you simply calculate this. So your resistance is just your input resistance anyway. So that's why it's so simple to get the input resistance. Okay. Now for output resistance, it's going to be a little bit tricky. I'm going to get to, actually, I should have the slide over here. So to get output resistance, what we need to do is also, we do this. For any like black box, we can apply a voltage like VO, and we get IO, or maybe we should use lowercase. And our resistance is going to be RO equal to VO over IO. Now, in this case, remember to short voltage and open here I want to make a notice that not controlled sources, because the controlled sources, unless like it's unless it goes to like zero or current or zero voltage, you shouldn't open or close it because you have to leave it there. That's important. You know, again, this a popular mistake is when a student see a current source. Oh, okay, I'm going to show this one. I'm going to open this one. I get like the output resistance. Well, sometimes you just get the right number because that current is actually zero. But in real life, it may not be necessarily zero, so you shouldn't open it before you do the inspection. Okay, so now let's do this equivalent circuit over here and try to see what happens. Okay, so if you look at this this circuit over here, we're going to do this circuit. At the input side, we would short the voltage source, so it's like this. Okay, and then at output side, the reason we have to draw the let me this time use a different word. I'm going to use R out. Guys, I'm going to change this to a different so that we don't get confused anymore. I'm going to use R out. So R out is going to be VO or IO. Well, you see what I did is I shorted the input voltage. I even left the R6 in the circuit, even though it's not a part of the equivalent circuit. I have to leave it there because otherwise my circuit is actually not complete. And then I left the current source intact, right? And then I have all this. So what I'm going to do is I'm going to look at how much is the current source. Well, what is the current source anyway? How much is it? In terms of expression, you would have GM times what? Yeah, let's call it like Vx over here. So this is GM times Vx. That Vx could be Vg or Vgs or could be Vb, right? So since okay, number one, number two, and then number three. So since Vx is how much is it? You look at this loop, guys. Look at the loop over here. This is its own loop. How much current is in the loop? How much current? Zero. There's no voltage source. And ground to resistance. If it's zero, how much is the voltage over here? Zero. If that's zero, how much current is over here? Zero. If it's current zero, what do? Open it. Yeah, okay. Open it, right? So you can open it. So this is open. Oops, why it doesn't go to blue? It shows blue. But anyway, so you open that. Once you open that, what do you have then? At the output, you have RO, VO, and IO. So your input resistance I out, I mean, you don't have to even calculate. You know it's VO or IO, it's going to be your RO. In this case, I keep changing the actual. Right? So we got that output resistance is actually your RO over here. So it becomes very simple. Now, of course, our life is not always that easy. And these are really just the simplest circuit that you can get. As we move on, you're going to see more and more complex circuit, and the output resistance, it can be a little bit tricky to find. But anyway, so that gives you kind of idea how to solve for input resistance, output resistance. You know, for example, in this case, initially we didn't open it because we don't know whether it's zero or not because it's a control source. Until we find, yeah, it is zero. Now we can open it. If you have like a common, say you have a common collector amplifiers, and this will be connected, and then there's some resistance here, you'll find, yeah, no, that is actually not zero. You cannot open it. So that's why the output resistance changes dramatically. But we'll, of course, get to that point once we get to different areas. Okay, so now let's go quickly through just a few of this. Now this circuit, of course, we already did it. I mean, you guys, you know, can basically, again, you do this one, you come to here. We did the gain already, and then we know that the gain like becomes, you guys know that we O equal to this RD times GM times minus GM times RD times VI, which we are in this case, we sig. So your AV is VO over V sig is minus GM times RD. So that one, we already did it. But I think the step is that how do you find the input and output resistance? Well, you guys, in this case, we actually already did. So you guys know that our input resistance, what, is infinity, because really you look at input, it's open circuit, so it's infinity. And your output resistance in this case, what it did is because, I mean, ideally you guys should add like ROO here, which you know there's RO equal to VA over ID. So if that's the case, your output resistance will be simply RO and in parallel with RD. So that's a little bit tricky, guys, over in the future, because depending on what you're talking about output resistance, if we are talking about output resistance of the MOSFET, it should be RO only. But if you talk about the resistance of like the whole like equivalent circuit, including the DC biasing, and it will be RO in parallel with RD. Okay. If you don't consider RO, it will be RD. So that's really just that difference. So this is just like a recap the gain and also input output resistance. And if next we're going to go to common emitter. So common emitter really just almost identical to the MOSFET common source, but instead it has R pi. So we already did the gain. You guys remember the gain is going to be, well, the output is GM minus GM times V pi times RC. I'm going to add RO over here. So it's reach RO, you're going to have this one. That's your, but you know that the V pi equal to a voltage divider. So V pi is R pi over I pi plus R sig times V sig. So therefore, from here, you get your voltage gain. AV equal to VO over V sig, it's equal to minus GM times R pi plus R sig, and then multiply by RO in parallel. Yeah, there's not enough space. Let me write in the second line. Minus GM times R pi plus R sig, and RO in parallel with RC. Okay, so that's your gain. I mean, we did this many times. I just like recap so you guys recall what we have. And then for the whole overall circuit, we're going to look at the input resistance, output resistance. I mean, if you look at the output resistance, you guys look at this part of the circuit, and you can clearly see that R in equal to R pi. And we did that also in the previous slide. And your R out, we can do the same thing. Okay, we already did, because when we short this this voltage becomes 0, so this becomes open circuit. So our output resistance is simply, in this case, it's going to be RO in parallel with RC. That's your output resistance. So those are two, I would say, the common source, common emitter, that's the most, there's the simplest amplifiers, and then they're also most commonly used amplifiers. And you got the gain, you got input resistance, you got output resistance. And you can see that the output resistance is similar for both MOSFET and BJT, but for input resistance, MOSFET is infinity, and BJT is R pi. So that's what we have, common source and common emitter. Now we're going to get into common source, but we have a resistance at the source. So you might say, well, strictly, this is not a common source because source is not grounded. There's RS, but instead of inventing another name for this, but they simply call it common source with a resistance as a source. So it can be the long, but it works. So for this circuit, we can, what I want to do is we're going to start with the pi model to see how it complicate the process, and then we come back to the T model and then to see how easy that helps. But of course, the important thing is that we want to find the input resistance and output resistance as well, not just the gain. We want to find that as well. So from now on, you're going to do that. So let's look at the circuit over here. Well, no, that's your MOSFET. So we're going to take the MOSFET out. We're going to draw the equivalent circuit. Now you notice that I started to draw RO in the circuit because, really just make it complete instead of going without RO and then come back with RO. So we just have RO. Okay. So now we see what is connected to the input, and we should do this together. And then you see your input has a resistance. And then your output has RD. So also connect to ground. And then the only difference now is you have RS at the source. That little RS make your life, like miserable, because the reason is when you look at the voltage gain, you look at here, is GM times VGS. And your VGS is from here to here, but your RS. So in this case, we know that your VGS is equal to at least it's not equal to V sig. Even though the RSIG is kind of open circuit. You look at from the first color, you might think, oh, VGS and V sig, are they in the same circuit? Yes, they are in the same circuit, but it's not equal. Why? Because VGS, the bottom of VGS is not ground. The ground is actually at the bottom of RS. So if you do a loop analysis, you would find this. So what it means that really we can say VSIG equal to VGS plus GM, the current, times RS. You see what I mean? current flows into RS, that current is GM times VGS. And you multiply by RS, you get the voltage at the bottom. And your VSG is VGS plus RS, the bottom voltage drop. So that's 2. So from here, of course you can easily derive. You can derive the relation between VGS. So VGS is 1 over 1 plus GM. So you find this one. So we can, just like the equation, we have VGS on that side. So we simply verify that the GM times RS. So we get that VGS is that one. So now once you find that, and you will say, well, maybe we'll do it here. So then we can say, well, our VO is minus GM times VGS times RO in parallel with RD. Right? So the output VO, I should have marked it on the circuit over here. So VO is the current multiplied by the two resistance in parallel. So you might say, oh, what happens with RS? Well, it doesn't matter because RS is ground on the outside. Well, VO is really just from ground to VO. So from ground to VO, you have current flowing up and then flowing down on the other side, right? So you have VO is minus the current multiplied by RO times RD. So now we plug in VGS. So VGS 1 over 1 plus GM RS basic. So now we can say that AV equal to VO over VSIG equal to minus GM and RO in parallel with RD. Okay, so by this time you already realize that, yes, if you have a resistance at the source, your gain in comparison to the one without a resistance source, it did reduce by this much. It reduced by this much. Now, depending on the value for RS, and this number could be, it actually could be pretty big. Again, it depends. Okay. So if this number is big, and then your gain will be reduced by a certain percentage, maybe half, maybe 1/3 or 25%, whatever the number is. So we can still do it. So with the pi model. But of course, so what happens is in the future, if it's a BJT, it becomes more complicated because that's no longer open circuit, you have R pi over there. And the current is no longer like a GM times V pi, but actually it's IB plus IC goes to IE. And so we're going to get to that, probably not today, but we'll get to that point. So that's what we did with this pi model. But if you can do this one also with a T model. So I'm not going to redraw the T model, but you guys can follow through. So you find the MOSFET, you find the T model, you connect every component to the different terminal. So like on G side, you have this. And on the S side, you have RS. At the output side, you have RD. So the only thing I want you to add is RO. I want to add RO over to here. And my RO will be connected to between D and S, okay? So if I do that, instead of using pi model, you're using T model, actually you would find this actually multiplicative. Why? Because the RO no longer, it's not a ground, it's actually connected with S. So this actually makes your like life a little bit more complicated. And without RO, actually it's simpler. Yes, it does. Okay. So the other thing to remember is no current into the gate. Okay. So that's something you got to remember. Now this connection, even though there's no current, we still connect it because we connect means the potential over here and over here are the same. If you open this one, it becomes like misleading because we don't know whether the voltage over here and over here are the same. So you can do the same procedure, and then you can find the actual gain will be similar. But so you can do it, but I'm not gonna, so today we're gonna skip that one. But what I wanted to go further is we want to find out what is the input resistance and what is the output resistance. So let's go. So let's start with, maybe here. And number 7, I'm gonna find out. So how much is the input resistance? If you guys look at the equivalent circuit, whether it's T model or pi model, by definition, how do we calculate Rin? Remember, that's what we did. We apply voltage and we find the current and we divide them. So in this case, when you apply voltage at input side, what do you get current? 0, right? So therefore, your input resistance is infinity. So that's, again, that's a beautiful MOSFET. The input resistance is infinity, which is really good, okay? Now we're gonna look at the output resistance. So for output resistance, what we're gonna do is we're gonna short the input. I'm still going to use the pi model because I found pi model with RO is actually, oh, you know what, guys? I made a mistake. I'm sorry about that. So the RO is actually not, is over here. It's not grounded. So in this case, this, yeah, probably, you know what we're gonna do is we're gonna, you know what, I'm gonna do the RO later. So let's guys forget about the RO. Let's do that. So if I don't have the RO, guys, change this one to just RD for now. Sorry about that. I was looking at this and immediately I figured out that there was a mistake. So our out is going to be final. So this is RD. We can always bring that RO back at a later time because today I don't think we have that much of time to do that. So when we find RO, okay, what we're doing is we are shorting the input voltage, but we keep the current source over here. The reason we keep it here because we don't know whether that current is 0 or not. If it's not 0, it's something. But if it is 0, we can open it and it will be simpler. But in this case, actually, it is not 0. Why is it not 0? Because even though the input is grounded, our current is GM times the voltage over here. But the voltage from here to here is not 0. Now, because this is ground, what voltage do you have here? 0. So yes, so your voltage over here is 0 volts. So like this one is almost ground. So all VGS, so all VGS equal to 0 minus, let's call it VS. And then VS equal to GM times VGS. Oh, something is not working properly here. VGS, VGS, whew. How can that work? Yeah, sorry about that. I confused myself. So VGS is coming there, and VGS, GM times VGS times RS give you that voltage. It's minus VG. Oh, it's actually should be VGS is equal to 0 minus VS, and VS is GM times. So this one says VGS. So look like we got, no, this definitely is not right. I'm gonna probably, let me work on this. I'm gonna get that probably, I'll get that correct instead of figuring it out. I'll let you guys, we're gonna move on, get that next time. So for the common emitter amplifier, it's very similar, but also again, the pi model will become really complex because there's going to be like the R pi, and then there's RE at the bottom, so it'll make it more difficult. So we stick with the pi model for this one. But in the meantime, I think what I'll do is I'll also give you the pi model equivalent circuit, just so you see how difficult that can be. Again, as I said, it really is saying that, yes, you can do it, but it becomes more difficult because you got like a node at the emitter, you have 3 connections. So that's what it makes more difficult. By doing this T model, it makes it a little bit easier. Again, you guys remember when we did the T model, there's RE at the bottom, that's current up there. And so in this case, we can find the gain by doing, so using this T model, we have VO equal to minus alpha times IE times IC. Then IE equal to so this alpha times IE is induced current, but we need to find IE is actually over here. Now, to find IE, so you need to find actually the voltage over here. But what we are doing is we have a V sig over here. But this circuit over here is actually, even though we can write a loop equation, but remember they don't have the same current. So this is IB, but this is IE. So if we write the loop equation on that loop, what we are finding is, so this is the loop equation over here. It's called number 2. So we have V sig equal to IB, the voltage drop on that input resistance, and then plus oops. Yeah. So you see, when we write the loop equation, we just make sure that we use the different current at a different branch. Now, of course, we know there's a relation between IE and IB, right? So we know that, IB, you guys know that, for example, IB is IC over beta, and IE is IB plus IC. So and then you replace IC with so this is 1 plus beta times IB. So you have IB equal to IE over 1 plus beta. So you can plug in this one into this equation here, and then you can find either IE or IB. So you can find IE. There's a certain expression. So I'm gonna leave it like that. And once you find IE, you plug in this back into. So you plug in this into minus alpha times IE times RC, and then there's a certain expression here. So I'm going to just also leave it like that. What we're going to do, or you guys can go ahead and derive the actual expression of those. So what we're going to do is we're going to look at again, the input and output resistance. So when you do that, you would similarly, you would mark, like in this case, for example, when we look for the input resistance, and the kind of you need to short the voltage, open the current, but there's no other voltage or current source in the circuit, so there's nothing to open other than the control source. But you cannot open the control source unless it's 0, so we will leave it there. So when you leave it there, how do you find this, like VI, right? You use VI, and then you divide by this current, and you will find the input resistance. So in this case, you can say that your VI is actually IE times this one, right? So your IB is over here. So what we write it is that, all right, so we have, so this is our, now we're going to connect V in over here. So in this case, you can see that you use the loop analysis, you will get V in equal to IE times IE plus IE times RE. And we know that RE equal to, just remember, we already have RE equal to this one plus B, oops. So we plug in over here. So we got V in equal to we get R in, equal to V in over I in, which is equal to V in over IB, and equal to and this one you can further so we get the input resistance. In fact, in this case, we got input resistance instead of R pi, it's actually amplified by this much. Now remember, this number is usually big, like RE maybe in the kilo ohms, and your 1 plus beta is 100. So immediately you increase your input resistance by something like, you know, if for like a R pi is say 10K and RE is 1K, but beta is 100. So you get your resistance R in is 10K plus 101K. That gives you 111K. And you can see your input resistance increased by 10 times, which is a good thing. So that's why connecting a resistor at the emitter is not a bad thing, because it does help you to increase the input resistance. Okay. So I think if we for the common source amplifier, like well, that one we already have the input resistance to be infinity, so there's nothing to worry over there. To find the output resistance, so let's get to that next week, and we're going to stop it here. So next week we're going to come back with the common source and common emitter output resistance, and we're going to look at common gate and common drain as well. Hopefully, you know, we have time also to go to the DC biasing, you know, on Tuesday, and then on Thursday, we're going to finish up the chapter. Yeah. So, okay. Well, with that, have a happy Thanksgiving. I'll see you next week.